Alright, so video interruptions and all that. Let's go ahead and move on. This is dynamics of circular motion, video part 2. We're just going to continue on with saying, I left off saying that there's no centripetal force. It's not a new magical force that makes things turn in a circle or move around the center of a radial pathway. It's just other forces that happen to have their net force pointed in the direction of a circle. So for uniform circular motion, if there's an acceleration, then the net force will be proportional to the mass, and that means that the net force and the acceleration, since they're both vectors, will both point toward the center of a circle. So we can establish definitively, if an object is changing directions, there is a force. If the only thing that's happening is changing directions, then you've got a centripetal acceleration only, and it's caused by a net force that we would call a centripetal force. And so that centripetal force will cause a centripetal acceleration. There's nothing special about this situation. It just so happens that when you calculate it out, the net force and the acceleration point toward the center of the circle. So you have net force equals mass times acceleration. They're both centripetal, so the centripetal acceleration is v squared over r. So a centripetal force, which is a net force, let's not forget that that centripetal force will always be a net force, is equal to mass times velocity squared over radius. This isn't an equation on your equation sheet, but it is something that you can easily place in by just remembering this relationship. So let's go ahead and let's look at an application of this. We're going to be looking at the force on a revolving ball moving in a horizontal circle. So we're going to be looking to find the centripetal force, which is a net force of a ball with a mass of 0.150 kilograms revolving in a circle of radius 0.600 meters at a frequency of 2 revolutions per second. Now I identified this as a frequency because it's per second, and 2 revolutions per second means that the period is 0.5 seconds, or the inverse of that. So here is our object. It's moving in a circle. Here I've pointed, if it's moving in a circle, then you know that you have your centripetal acceleration. If I assume that this ball is turning clockwise, then it would have a tangential velocity like this. But what we need to do is we need to establish for this ball moving in this pathway what the free body diagram looks like, because you know, you've got this hand. This is what hands look like, and it's holding a string, and that string is attached to that ball like so. And that string is causing that ball to move in a circle. And notice that I did not draw that string straight up and down, because that string will be experiencing a force on it. Specifically, it will be experiencing the force of tension. And we know that that's true. But that ball exists on Earth, so that ball has weight. So there is yet another force down here, the weight of the ball, mg. And you notice I had that arrow in there as the centripetal force pointing toward the center. It's not quite completely pointing toward the same direction as the tension, because establishing our axis, right, if this here is the tension on the ball, and this here is the weight of the ball, then right, this is the axis, and this will be the net force. And that net force, right, of by vector addition, will be pointing toward the center of the circle, and that will be equaling mass times acceleration. So that means that when we do this, we could break this down into the x and the y axis. But let's consider, we're going to make a quick assumption, and then we're going to check and see if our assumption is correct. Oops, I'm way out of your guys' screen. Sorry about that. We're going to assume that the weight of this ball has very little magnitude compared to the force of tension. And so what we're going to do is we're going to solve for the net force, and we're going to see how close to the net force that force of tension is. So what we're going to do is we're going to say, well, we know that since the ball is traveling in a circle, we know that the net force that the ball experiences that causes that acceleration is a centripetal force, and it will equal mv squared over r. For this ball, v is going to equal the circumference, 2 pi r over t. So that's an easy solution. It's going to be 2 pi times 0.600 meters divided by 0.500 seconds. So we end up with a velocity of, bear with me here, 2 times pi times 0.600 divided by 0.500, and we get a velocity of 7.54 meters per second. So if I want to plug that into this equation, then I get that the net force is equal to the mass of the ball, 0.150 kilograms, times 7.54 meters per second squared divided by 0.600 meters. That will give us the net force. So I'm going to square that velocity, times it 0.150, and divide it by 0.600 to get a net force of 14.21 newtons, which I'm going to report to two significant figures, 14 newtons, based on our original values. You might be able to do 14.2 newtons. Now remember, this is not the force of tension. This happens to be the net force. So we're going to compare this to the force of tension now by saying, well, the force of tension is skewed or offset by the weight of the object. Specifically, the y value is offset by the x value. So mg for the ball would be equal to 0.150 kilograms times 9.8 meters per second squared. Right? That is the weight of the ball. So the weight of the ball is 1.47 newtons. And that's only skewing the y direction of tension. So at some very small angle, that's an incredibly small amount of force. It's actually, if you look at 0.147 versus 14 newtons, that's 1/10. All right, the value of the overall net force that we're looking at here. So that means that our result is only skewed by 1/10. It's not really going to change this value. So we could say that the force of tension from the string is about 14 newtons, and we've got 1/10 of accuracy. So it would be actually 14 newtons plus or minus about 1.4 newtons. And that would give us, within a correct amount of significant figures, the correct value for the force of tension, just assuming that the force of the weight of the object doesn't skew it that much. So that's a really neat thing that we can do for something swinging in the horizontal direction. But there's not just horizontal direction for circular motion. When we're on Earth, gravity has a huge effect on anything traveling in the vertical direction. So the next thing we're going to take a look at is we're going to take a look at solving for a vertical object. And so I have here the problem, the vertical octopus. In the problem, it's a revolving ball. We're just going to say that this ball is an octopus, because why not? There's its, and there's its happy little eyes, and there's its happy little eyes, and now the problem is cute and easy to solve for. Now, we've got for this circle, we're going to say that this circle, I'm drawing it over here to get out of the way, has a radius, a continual radius of 1.10 meters, and the mass of the octopus is a continuous 1.50 kilograms. Now, there's two things that we're going to be solving for. The first is we're going to be solving for the minimum velocity up here for the octopus to continue in a circle. And we're actually going to be using a free body diagram to take a look at that, because for a centripetal motion or circular motion, the net force equals centripetal force equals mv squared over r. So we can solve for velocity using a free body diagram if we could only resolve all of the net forces. Now, a really important thing to look at, if we're swinging this octopus in a circle with a string, then that means that the velocity down here is not going to be the same as the velocity up here because you've got gravity acting as it travels up and down the circle. As it goes up the circle, gravity is going to act in the opposite direction of its velocity, slowing it down, so it should be slowest at the top. And then as it falls back down the circle toward here, the velocity should be the largest at the bottom. So this is not uniform circular motion. However, if we isolate each of these points and treat this point as different from this point, then we can apply this equation as though that one instant it's experiencing uniform circular motion, and then we don't have to consider any acceleration of the ball as it travels tangentially along that pathway. So we need to decide for this octopus what forces it's experiencing at the top and at the bottom. So one thing I know, anything on Earth always experiences its weight. So in both of the free body diagrams, I'm going to give it its weight force. And then it's getting swung around in a circle by a string. So that means that up here, the string, right, is always connected to the center. So here you've got another force down, and it's the force of tension. And down here, you've got the force of tension pointing up. So you can see that the free body diagram for the octopus at the top and the bottom of this circle are different. And it's because of the direction of the tension, right? The direction of the weight of the octopus never changes, just like the direction of the weight of an object never changes as long as you're on the surface of the Earth. So our free body diagram for the octopus at the top is two downward forces, force of tension and weight. And down here, we've got the force of tension up and the weight down. Now we establish our axis system. Since we're dealing with a circle, we're just going to say anything that points toward the center of the circle is positive. So for this one, when we're creating, we've got one direction, one axis here. Isn't that nice? We're going to do the net force for the top is going to be equal to, both of these are pointing toward the center of the circle, so both of them are going to be positive, force of tension plus the weight of the object. And here, we're going to have the net force equaling the force of tension, which is pointing toward the center of the circle, minus the weight of the object. Now, both of these equal a net force, so both of them equal ma. Since we're dealing with circular motion, they're going to be equaling specifically centripetal acceleration, so mv squared over r equals mv squared over r. I love the symmetry of this problem. It's so clear to see why these are additive and why these are subtractive, as long as we remember pointing toward the center of the circle is positive. So solving. Now we have to look at some concept or situational things about this problem. And one of the things that we want to look at is at the top it says we need to know the minimum speed of the ball that it must have in order to continue moving in a circle. So if the ball is going at the top, the two forces are the force of tension and the force of gravity. And as long as that tension is taut, right, the more tension there is, the more net force that will be toward the center of the circle, which means there will be more acceleration toward the center of the circle. It will change directions more quickly if there's more tension. And if it's changing directions more quickly, it means that there's more velocity. We're looking for the minimum amount of velocity for it to travel in a circle. The minimum amount of velocity means the smallest amount, which means the smallest amount of tension. And so here is where we're going to think about it. And we're going to say, well, the smallest amount of tension that something could have, if the string went completely slack, the octopus would fall back down. However, if the string was just at its absolute minimum, then that means the minimum velocity will occur when the force of tension equals 0. Right? And we're not assuming that the tension is so slack that the octopus falls down. We're going to assume this is just like the moment it has, the tension is dropping, and at the very top it's 0, but what happens? It begins to fall down, so the force of gravity accelerates the string, accelerates the octopus, gives it more velocity, and it goes back around. So that means the minimum velocity will occur when the force of tension is 0, which means we get to drop a 0 right here, and we love dropping zeros. So there we go, and we get the equation mg equals mv squared over r. You know I love it when mass cancels out. So that means that the velocity is going to be independent of the object's mass, just like most things that depend on the force of weight to an object. So that means that the velocity is going to equal the square root of gr. And if I plug in 9.8 and 1.1 in there, then what I should end up getting is a value of 3.28 meters per second. And that is the minimum velocity for the octopus to continue on its pathway and begin accelerating again toward the center of the circle. For part 2, it says find the force of tension at the bottom of the circle, assuming that the velocity at the bottom is twice the velocity at the top. Well, twice the velocity at the top is actually going to be a velocity of 6.56 meters per second. So here, our velocity is 6.56 meters per second. And we're going to use that to solve this equation. So I've got force of tension, which is my unknown that I want to solve for, minus mg equals mv squared over r. I'm solving for force of tension, so I'm going to add my mg to both sides. I'm going to go ahead and say ft equals mv squared over r plus mg. Now here my m's stick around, so I have ft equals 0.150 times 6.56 squared divided by 1.1 plus 0.150 times 9.8. And I do that math, I calculate it out, and I get that the force of tension equals 7.34 newtons. So the force of tension at the bottom is actually substantial. There's a couple other things that you're going to look at in this chapter as far as examples go, but there's really just a couple of things that I want you to focus on as you're solving problems for circular motion, right? We're still dealing with acceleration, and we're still dealing with net forces, which means that absolutely across the board you are not going to solve a circular motion problem without drawing a free body diagram and considering all of the forces that should exist in this situation. It's really important to do this because otherwise you're not figuring out what your net force is coming from. If you've got uniform circular motion, you've got a net force. That doesn't mean that you're necessarily solving for the force that's asked for. So that means that the next thing you want to do is determine which of the forces or the components are providing the centripetal acceleration. Just like we did for the horizontal circle, right? We said, oh, force of tension and the weight of the object result in that net force, and then we determine how much of a role the weight played on the object in that circle. For the vertical octopus, we said, oh, here the centripetal force is gravity and tension. All right, but at the bottom, it's tension and weight, and that means that the product at the bottom is going to be a subtraction, whereas the product at the top was going to be additive. And so it's really important to have your free body diagrams and establish where is my net force really coming from, because my net force isn't a brand new centripetal force, it's a product of our free body diagrams. And that means that we're going to have to always choose a convenient coordinate system. Our convenient coordinate system for circles is pointing toward the circle as positive. Right, and you'll always do that even if you're solving part 1 and part 2, and that means that you make up positive in part 1 and down positive in part 2. You're just always going to choose toward the center of the circle as positive. And remember that your radial acceleration, or your centripetal acceleration, is v squared over r, and that means that you're just plugging that in into your F equals ma Newton's second law equation. And then you're going to use what you know about resolving free body diagram equations and applying Newton's second law to then solve for any individual pieces in an equation. And that's it. You're ready to go.